Good afternoon and welcome to Webinar Wednesday. We're excited to have over 300 registered attendees for today's webinar, which is eligible for 1 credit from the ACI. Let's get started by giving one lucky attendee a Webinar Wednesday t-shirt for answering this trivia question. In Charles Dickens' novel, A Christmas Carol, what was Scrooge's first name? Answer now using the questions feature on your dashboard. While you're answering, I want to invite everyone to save the date for 2 of our expos next year. First, for our ICE Imaging Expo, which will take place at the Hilton Scottsdale Resort in Scottsdale, Arizona, February the 9th to the 11th, which will bring imaging service professionals from across the nation for 3 days of learning, networking, and the latest advances in imaging. Registration is open and more details can be found at attendice.com. Also, our Spring MD Expo, which will be taking place at the Hotel Irvine, California, from April the 20th to the 22nd, which will bring together HTM professionals from across the nation. So more details can be found at mdexposhow.com. Okay, and let's see who the winner of our Webinar Wednesday t-shirt is. And it is, oh, hang on a minute, let's have a look. It is Robert, oh no, forgive me, sorry, it's Jose Carrillo. Congratulations, Jose. It is, the correct answer is Ebenezer. Okay, Webinar Wednesday would like to thank our sponsor, Philips. Philips has built a reputation for best-in-class support that's right-sized to your needs. Ultrasound services have ranked #1 for 26 years in a row, first in overall performance, and 34 other categories based on customer rankings in the 2018 IMV Service Track survey, which means you can expect their solutions to work today and into the future. For more information, visit usa.philips.com. Okay, today our presenters are from Philips, so I will hand over to Terri Richardson, Senior Global Product Manager, to introduce the team. Terri, you may begin whenever you're ready.
Thank you, Linda. So welcome to Webinar Wednesday, everybody. We're really happy to be here with you today. As Linda said, I'm Terri Richardson, Global Product Manager. I also have a team with me today. I have Jim Moran, our North America Service Product Manager, Mark Potts, our Senior Global Service Product Manager, and our speaker for the day, Stone Dupree, Technical Trainer and Developer. In this session, Stone's going to give you a taste of one of the courses offered at our newly renovated Technical Education Center in Cleveland. The Philips Cleveland Training Center is a state-of-the-art academy that has 20 fully equipped classrooms and labs, along with over 200 instructors and field staff covering 9 medical modalities. So with that, let's go ahead and get started, and I'm going to turn it over to Stone for our Ultrasound Basics course.
Thank you, Terri. Hello, everyone. My name is Stone Dupree. I am one of the trainers for ultrasound service here at the Cleveland Training Center. Today, we're going to be presenting to you an abbreviated version of our US 9080 Ultrasound Essentials course. And if you have any questions, we'll be happy to answer those at the end of the material here. Let's start this course on ultrasound essentials with a very basic definition of sound. In a dictionary, you might find a definition being vibrations that travel through air and are audible to people. If you look and try to find maybe something more detailed, you might find something like it's a disturbance of mechanical energy that propagates through matter as a wave, or mechanical radiant energy that is transmitted by longitudinal pressure waves in a material medium, such as air. Let's break the last definition down into pieces. Sound produces oscillations of the medium through which the sound waves propagate. We normally think of the medium as air, but sound can actually travel in water, oil, metal, and many other solid materials. Sound cannot, however, travel through vacuum or empty space, as you probably know. Sound is defined as mechanical energy because the particles in the medium vibrate. Electromagnetic waves, such as radio waves and light, may travel through a vacuum, but sound waves require a molecular medium. In other words, an elastic, deformable medium in which to propagate. A wave is a traveling variation. For example, a water wave is a traveling variation in water surface height. Dropping something into a pond disturbs the water surface, causing it to move up and down. Similar variations for sound can be found in the air or other medium. The pressure variations in the sound wave cause particles of the medium to vibrate back and forth. The diagram shows a representation of a sound wave over the time axis. There are some parameters that will help us describe the wave, two of which being amplitude and frequency. The sound waves are called longitudinal because the particles in the medium move in the same direction as the sound. The sound can also travel at different speeds based on the density and stiffness of the medium. In this diagram, we see that there is a small sample of materials and the corresponding velocity of sound in meters per second. Note that the velocity of sound in the air is completely different to the one in wood or skull bone. Also note that the speed in liver, soft tissue, and water is about the same or very close. In this animation, we can see that the speed of sound depends upon the medium in which it's traveling through. Okay, so we have already defined sound, so now let's take a look at what ultrasound is. The word ultra means beyond. Ultrasound is a sound beyond the normal hearing range of humans. This is referring to a sound of more than 20,000 hertz. In medical ultrasound, the frequencies commonly used are between 1 megahertz to 25 megahertz. Medical ultrasound is a non-invasive way to look inside the human body using ultrasound signals. Ultrasound instruments transmit ultrasound pulses and then receive the echoes of the same pulses. Based on the time between the transmit and the receive, the ultrasound system will place a dot or pixel onto the screen. The brightness of each pixel represents the echo strength, and the location of the echo represents the location of the echo structure generating the return echo. Pulsed ultrasound is the most commonly used method for imaging ultrasound. In this way, a few cycles of ultrasound, separated in time, are sent to the body. There are some parameters that help describe the pulsed ultrasound waveform. Some of these are PRF, or pulse repetition frequency, PRP, or pulse repetition period, duty factor, and pulse duration. Knowledge of these parameters is important in understanding how ultrasound pulses and their resulting echoes are formed. An echo can be defined as the reflection of a sound. The reflected and scattered sound waves produce a pattern of echoes that is necessary for ultrasound imaging. This pattern of the echoes depends on the characteristics of the medium, such as the density of the medium and the propagation speed of the sound in that particular medium. There is one property that will help us understand how the sound interacts with the medium. It is called acoustic impedance. Acoustic impedance describes the relationship between acoustic pressure and the sound of particle vibrations in a sound wave. You will find that impedance increases if the density is increased or if the propagation speed is increased. When we are imaging using the pulsed ultrasound technique, the system cannot talk and listen at the same time. This slide provides an illustration showing the pulse, listen, receive process used in pulsed ultrasound. Later on, we're going to find that there is also a continuous wave technique, commonly called CW, and with that method, the system will continuously transmit and receive. Taking a look at this diagram, we see that ultrasound will travel until striking a structure composed of a different density and stiffness. We can see that some of the sound will continue and some of it will be reflected. The direction of the reflected echo will depend upon the angle of the ultrasound beam and then also the interface that's between the beam source and the echo structure. When talking about echoes, we're mainly talking about the reflection of a sound. The sound from one medium to the other can be reflected into the first medium or be transmitted into the second medium depending on the impedance. Also, instead of reflection, we can have what's called refraction. Refraction is a change in the direction of sound when crossing a boundary. There are some problems we need to be aware of while we try to image with ultrasound. One of them is attenuation of the signal. Attenuation is the weakening of the sound beam as it travels through the tissue. Attenuation occurs as a result of reflection, absorption, or scattering. Another problem with ultrasound is the scattering of the sound or redirection of the sound in many different directions as shown in the animation. Speckle is the generation of multiple echoes in different directions when the ultrasound hits a reflector. Both of these happen all the time in ultrasound. Fortunately, however, the ultrasound systems are made to minimize the effect of these. When we talk about reflectors, there are two main types. There is a specular reflector, which has a nice smooth surface, and a non-specular, which has an irregular or jagged surface. Reflected waves from these interfaces can scatter out in many different directions. With ultrasound imaging, there is a constant trade-off between penetration of the ultrasound signal and image resolution. A very important concept to remember is that if you have a lower frequency transducer, it will image deeper into the body, whereas a higher frequency transducer will produce a better image quality. It is important to use the highest frequency transducer possible to interrogate the region of interest in order to optimize image quality and diagnostic capability. This may require constantly changing the transducer during the course of the exam depending upon the region of interest. Remember, if penetration is needed, a lower frequency may be required. When imaging with ultrasound, there are some potential bioeffects that may occur. We need to be informed of these bioeffects because these effects can cause potential damage to the body. Ultrasound systems have been in the market for many years, and there are known appropriate ways to prevent or minimize these effects. There are two main mechanisms that potentially cause bioeffects. The first is thermal, or the heating of the tissue, and the second, mechanical, which is also called non-thermal or cavitation. There is a principle that helps guide in the reduction of the chances of tissue damage by bioeffect, and that is known as ALARA. ALARA is an acronym for as low as reasonably achievable, and it is a safety principle for the use of diagnostic ultrasound and other diagnostic imaging systems. Some think that reducing exam time is enough to reduce patient exposure to acoustic energy, but in actuality, the dwell time, which is the time a probe is actually on a patient when you are not actively getting an image for diagnostic purposes, is what must be reduced. Even though there are no known effects below a certain threshold, use of ultrasound should be restricted to medical necessity only. A couple of last points about bioeffects. First is, based on the exam type, there are limits of overall intensity. Second, it is very important to select the appropriate exam type and preset when scanning a patient. Selecting the wrong preset may unnecessarily expose the patient to higher intensities of ultrasonic energy. An ultrasound transducer consists of the following parts. The piezoelectric element converts electrical energy into sound and vice versa. Backing material damps the pulse and forces the wave into one direction. Matching layers are used to bridge the different acoustic impedances of the piezo elements and tissue. The lens is used to focus the beam and also as the footprint. Circuit boards inside contain electronics for various functions. Housing protects the inside. Strain relief is used to prevent the cable from pulling off the connector and transducer head. The connector physically connects the ultrasound system. Let's look at the piezo properties of ceramics in more detail. During the transmit stage, an electric voltage is applied to the face of the crystal and the crystal will deform. Depending on the polarity of the voltage, the thickness will increase or decrease. As a result of the deformity, the piezoelectric element will produce a sound wave. The terms transducer element, piezoelectric element, active element, crystal, or ceramic all refer to the piece of piezoelectric material. Ultrasound transducers typically are driven by one cycle of voltage, which produces a 2 or 3 cycle ultrasound pulse. The frequency of the sound produced is equal to the frequency of the driving voltage, which must be near the operating frequency or so-called resonance frequency. The operating frequency is determined by the following: the propagation speed of the element material and the thickness of the transducer element. During the receive stage, the returning sound wave, the echo, will deform the piezoelectric element. As a result, the element will produce an electrical signal. In ultrasound applications, the driving transmit voltage is about 100 volts. The voltage produced by the element during receive is in the range of millivolts and microvolts. The operating frequency is such that the thickness corresponds to half of a wavelength in the element material. Thinner elements produce higher frequencies, and thicker elements produce lower frequencies. A variety of ceramic piezoelectric materials are used to create the ultrasound transducers. One of the most popular is PZT, or lead zirconate titanate ceramic, where the fine powders of the component metal oxides are mixed and then heated to form a uniform powder. The powder is mixed with an organic binder and baked into a dense polycrystalline structure. Notice that the texture is not perfect, as you can see on the right. New research has resulted in the development of other types of materials that also present good characteristics for ultrasound imaging. One example is the Philips PureWave element, which you can see on the left side. Because the transducer element is a solid, it has an impedance that is about 20 times that of tissues. Without compensation, 80% of the emitted intensity would be reflected at the skin boundary. To solve this problem, a matching layer commonly is placed on the transducer face. Its function is to improve sound transmission to the body, reduce the reflection of ultrasound at the element surface, allow most of the ultrasound energy to exit the front of the element. The impedance of each matching layer is of intermittent values to compensate the impedance of the elements. Typically, 2 layers are used, but 1 or 3 is also possible. Next to the matching layers, the lens also acts as a matching layer. This is a real picture of the layers inside the transducer. You can see the backing material, the piezo element, the 3 matching layers, and a ground foil. Depending on the operating frequency, the thickness of the piezo element is approximately between 0.1 and 1.0 millimeters. In this picture, you can see the size of the elements compared to a human hair. During manufacturing, these layers are all glued together and to the backing in large pieces. Once they are glued, the stack is diced or cut through to create the acoustic elements. Every acoustic element is also diced to create sub-elements. The purpose of the sub-cutting is to improve the acoustic waves. Sub-elements of the same acoustic elements share the same electrical connection and therefore are fired at the same time and act together as a single element. The backing material is a mixture of metal powder and a plastic or epoxy. Without damping, a transducer element produces a long ultrasound pulse of many cycles. With damping, on the rear of the face of the transducer element, a short ultrasound pulse of a few cycles is produced. The shorter the pulse, or the fewer number of cycles, the more frequencies present in it, or the broader the bandwidth. A shorter pulse also improves resolution. This will be explained in more detail later on during the resolution section. Typically, pulses of 2 or 3 cycles are generated with diagnostic ultrasound transducers. Transducers resonate at a primary operating frequency, but the pulses produced contain a range of frequencies called the bandwidth. A narrow bandwidth means that the transducer can only operate effectively over a narrow range of frequencies. For example, a 5 MHz transducer with a narrow bandwidth may not work well below 4 or above 6 MHz. The lens or footprint is part of the transducer that contacts the patient. The footprint functions as a matching layer and as a lens for the short axis. Because of its very low impedance, even a thin layer of air between the transducer and the skin surface reflects virtually all the sound, preventing any penetration into the tissue. For this reason, gel is used as a coupling medium. This eliminates the air layer and enables efficient passage of the ultrasound into and out of the tissue. An ultrasound beam consists of a beam width in two directions, the short axis and the long axis. In the short axis view, we can separate different zones. The region from element to minimum beam width is called the near zone, near field or Fresnel zone. The near zone length is determined by the size and operating frequency of the element. The region beyond the minimum beam width is called the far zone, far field, or Fraunhofer zone. Even with a rectangular unfocused element, there is some beam narrowing, called the natural focus. To improve resolution, transducers are designed to focus by using curved elements or using a lens. Notice that with focusing, the focal length and beam width in the focal zone become smaller, and the beam width beyond the focal point becomes larger. In the short axis view of a transducer, the focus is mechanically fixed by the transducer design. In the long axis view, the beam can be focused and steered electronically. This will be discussed later. All elements of a linear transducer are not excited the same. The array is divided into subsets or groups of elements called aperture. Aperture is a group of elements which are excited simultaneously. The echoes are then used to build up one line of image. The same principle is used on curved transducers as well. A phased array transducer uses no aperture. All the elements are fired to form one line. However, they are not excited simultaneously. Slight delays are introduced with a given sequence. This sequence and the delays are arranged to move the beam through an arc-shaped pattern. With a small aperture, fewer elements used, and the focus is closer and more superficial. With a large aperture, more elements are used and the focus is deeper. The purpose of narrowing an ultrasound beam is to improve lateral resolution and image quality. It is most effective in the near zone and at the focus. Focusing can be accomplished in one of a few different ways. One, by placing a lens on the transducer, or by cutting or curving the crystal, or, for non-conventional functioning, by electronic or array beam forming, which we'll explain in the next slide. When voltage pulses are applied in rapid progression from left to right, one ultrasound pulse is produced that is directed to the right. A similar pulse can be produced and directed to the left as well. A curve in the phase delay pattern results in focusing the pulse. A greater curve delay pattern, with longer time delays between the elements, moves the focus closer to the transducer. Conversely, shorter delays move the focus deeper. The more elements are used, the bigger the aperture, and the better the beam can be controlled. Multi-zone transmit was developed to get optimum focus over the entire depth of the field. Several transmit pulses are sent for each line, each focused at a different depth. Then, the final image is formed out of the portions of those partial images that are most in focus. This has the disadvantage of reducing the frame rate. Resolution is the ability to distinguish and display two objects as separate objects and is a measure of the system's image quality. Imaging resolution has three aspects: detail, contrast, and temporal. Contrast and temporal resolutions relate more directly to the actual ultrasound instrument. Detail resolution relates more directly to transducers, and that's what we'll discuss here. If two reflectors are not sufficiently separated, they produce overlapping echoes that are not separated on the image display. In ultrasound imaging, the two aspects of detail resolution are axial and lateral. The smaller the axial and lateral resolution, the finer the detail that can be displayed, and the closer two objects can be separated. SPL, or spatial pulse length, is the length of a pulse from its front to its back. SPL is measured in millimeters. Because wavelength decreases with increasing frequency, SPL decreases with increasing frequency. Shorter pulse length improves resolution. Common pulses have 1 to 3 cycles. Axial resolution is the minimum reflector separation required along the direction of sound travel to produce separated echoes. To improve axial resolution, spatial pulse length must be reduced by increasing the frequency. With an increase of frequency comes a reduction in penetration, or image depth. Other names for axial resolution are longitudinal resolution, axial resolution, radial or range, and depth resolution. Lateral resolution is the minimum object separation in the direction perpendicular to the beam direction, or that is, across the scan line, that can produce 2 separate echoes. Lateral resolution is equal to the beam width in the scan plane. Inside the transducer are some electronics, one of which being the transducer ID. This contains the identification process to identify to the ultrasound what kind of probe that is being connected. Additionally, if the number of elements inside the transducer exceeds the number of wires available or connections, multiplexing is used to route the signals. Multiplexing is a method used to reduce the number of channels used in the cable of the transducer. One wire is used for signals from different elements, and they are timed in the appropriate sequence to send to the ultrasound system. In our example, we use a multiplexer with 12 elements and 6 channels, and also scan with an aperture of 3 elements. At first, elements 1 through 3 are routed to channels 1 through 3, elements 2 through 4 to channels 2 through 4, etc. When element 7 is used, this signal is passed to channel 1, as you can see in this animation, and then continues the process from there. The elements in a linear array transducer are rectangular in shape and arranged side by side in a straight line. Applying voltage pulses to a group of elements produces each segment of the beam. In this illustration, a voltage pulse is applied to a group of elements at the same time. For example, elements 1 through 6 will fire, then 2 through 7, then 3 through 8, and so on, until the end of the array is reached. In an actual transducer, this process repeats several times per second. The speed of the illustration is much slower by design, so you can see how the beam forms. Notice that the field of view is rectangular in shape with a flat top. Applying voltage pulses to groups of elements in rapid succession is referred to as electronic scanning. When the process repeats rapidly enough, a real-time presentation occurs. The number and size of the elements in combination with how the groups of elements fire impacts the number of scan lines or line density in the image. A 250 line density image has better image quality than a 128 line image, as example. A curved array transducer works just like a linear array. The elements in a curved linear transducer are rectangular in shape and arranged side by side, but in an arc. The direction of the pulse changes due to the curved elements. In the linear array, the pulses go straight down, while in the curved linear, the pulses angle out to the side. Notice that the fan-shaped field of the view with a blended top becomes wider as it moves away from the scanning surface. Usually a curved away transducer is combined with lower transmit frequencies as the application that is used requires deep penetration. As a side note, during manufacturing, the linear array stack is bent in the curved shape of the transducer, as you can see in the illustration. Some properties of the curved linear transducer are a wide field of view and difficult to use in small acoustic windows, such as the chest cavity. Here we have two examples of curved probes. A traditional convex or curved probe on the left, such as used for abdominal studies, and on the right we have one for transvaginal or endocavity studies. Mechanical transducers are linear or curved transducers. The array stack and lens can be moved by using a motor inside the transducer to move it back and forth. Here you can see the inside of a mechanical 3D probe. Here is the array, dome, and fluid chamber of a Philips 3D6 to 3D probe. This is a 3D6 before the cable is attached and the housing is installed, and showing, among other components, the motor. In a sector transducer, also known as a phased array, the elements are arranged in a straight line as they are in a linear array. The difference is that the array is extremely small and the voltage pulses are steered. The voltage pulse is applied to all elements at the same time, but with small time delays or phasing. These delays result in the beam going out in different directions. The firing sequence repeats with a different time delay, thus changing the direction of the beam. Using time delays to sweep the beam from one side to the other results in a sector or pie-shaped field of view. A phased array is actually a linear phased array, but is commonly referred to just as a phased array or a sector transducer or probe. A phased array transducer uses no aperture. All the elements are fired to form one line. However, they are not excited simultaneously. Slight delays are introduced with a given sequence. The sequence and the delays are arranged to move the beam through an arc-shaped pattern. The main application for sector transducers is cardiac imaging because of the small footprint in combination with the higher frame rate. Unlike other imaging transducers, X-matrix transducers have square elements instead of rectangular. This image is a magnified X-matrix array showing individual elements and a human hair for scale reference. Depending on the application and design, it may contain up to 9,200 elements. Matrix transducers have technically the same principles as sector transducers, but a matrix transducer consists of much more elements and have elements in two directions in a matrix pattern, while other transducers use an array. With the X-matrix transducers, you can control the beam in any direction using X-plane. Initially, these transducers were developed for echocardiography. Now they can also be used in general imaging as well. Depending on the type of X-matrix, you can use all the modes with one transducer, whether it be 2D, 3D, or 4D, which is live three-dimensional imaging, live X-plane, Doppler, or color Doppler. Continuous wave, or CW transducers, emit sound continuously. There are two elements within the housing, one that continuously emits sound and one that receives. CW capability can be combined with an imaging probe, however, continuous sound cannot be used for imaging. Pulsed wave, or PW, non-imaging transducers are used when the correct location of the vessel must be identified. Pulsed wave transducers are low-frequency Doppler probes that emit several pulses along the scan line. They provide range detection, allow clinicians to choose specific areas of flow to analyze. Note, other names for these probes are PDOF, pencil, or static transducers. PW and CW probes are explained in more detail in the upcoming imaging section of this learning. Different manufacturers have different methods for naming transducers. Some manufacturers include the arrangement of the crystals and the frequency range in the name of their transducers. For instance, within Philips, a C63 is a curved array transducer using a frequency range from 6 to 3 MHz. Other transducers, L will stand for L for linear array, S for sector or phased array, X is for X-matrix transducers, V for volume, which is used for 3D and 4D transducers, and D for Doppler transducers. Ultrasound has the ability to work with more than 8 modes. Each mode has its own unique benefits and features as well as some disadvantages. The mode the sonographer will choose depends on the items of interest and the things he or she would like to see. These may include continuous wave, pulsed wave, color Doppler imaging, tissue Doppler imaging, color power angio or CPA, 3 or 4 dimensional mode or 3D 4D, and panoramic imaging. First, we'll start by taking a look at 2D or two-dimensional mode. This is used almost anywhere in the body and used in 80% of the studies, but it's particularly useful in the abdominal area. Next, we'll take a look at M mode or motion mode. This is useful for the timing of the movement of cardiac structures. Next is color mode. This uses color to represent the main velocity and direction of blood flow. Here we have pulsed wave Doppler or PW Doppler. Provides a spectral representation of the velocity of blood flow. This can use a single crystal or a set of crystals for transmit and receive. CW Doppler, continuous wave Doppler, is the same as PW, however, it permits higher velocities to be sampled. Next, we have angio or color power angio. It displays the magnitude of the color signal, not velocity or direction, though, very important. Next, we have panoramic imaging. This is used for larger parts of the body, such as the leg, for vascular type studies. This works much like the panoramic feature on your camera. Here we have 3D, three-dimensional, which is what most of us are familiar with obstetrics, the scanning of the baby, but we can use it for cardiac structures and other structures as well. Next, let's take a look at basic Doppler principles and how they are used in ultrasound to measure blood velocity and direction. Some of the modes, such as CW, PW, and color, require special techniques to display or measure the blood flow. Ultrasound systems use the Doppler effect, which is a theory based on the works of the physicist Johann Doppler. He said that there is an apparent change in received frequency due to the relative motion between a sound source and a sound receiver. If the sound source is moving towards the receiver, the received frequency will be higher than the transmitted frequency. If the source is moving away from the receiver, the received frequency will be lower than the transmitted frequency. Doppler is used in ultrasound to evaluate blood flow. The transducer is the sound source and receiver. The flow is detected by measuring the frequency shift relative to the transducer. Doppler produces an audible signal as well as a graphical representation of flow that equals the spectral waveform, as you see in the bottom of the screen. The movement of the blood flow produces a Doppler shift that is measured by the ultrasound system. In many cases, both the Doppler shift and the phase shift are measured. The spectral waveform represents the audible signal and provides information about the direction of the flow, how fast the flow is traveling, and the quality of the flow. Pulsed wave produces short bursts or pulses of sound. It uses the same crystals to send and receive the signal. This follows the same pulse echo technique used in 2D image formation. The advantages of PW are that it can sample at a specific site along the Doppler line. The location of the sample is represented by the sample volume. The disadvantages of PW are that the maximum velocity, which can be displayed, is limited. The signal will always alias at a given point based on the transducer frequency. Continuous wave uses different crystals to send and receive the signal. One crystal constantly sends a sound wave of a single frequency, while the other constantly receives the reflected signal. Color Doppler imaging represents blood flow in an ultrasound image and shows how to determine the direction. CW will send and receive constantly. This technique uses two different sets of elements on one transducer. PW sends a burst of waves and then waits for the returning echoes. This technique uses the same elements for sending and receiving. CD color is the same as the PW technique, but repeats many more times. So, what is color Doppler? Color Doppler uses the pulse echo Doppler flow principles to generate a color image. This image is superimposed on the 2D image. The red and blue display provides information regarding direction and average velocity of the blood flow. The velocity of flow with color is shown by the shading of the color. It provides information about the velocity of the flow. The deeper the shade of red or blue, the slower the flow, and the lighter the shade, the faster the flow. If the flow velocity is traveling faster than the lightest shade represented on the map, aliasing occurs. The color wraps to the opposite color. This aids in the placement of the sample volume for the sonographer. An imaging mode that we have not mentioned previously is harmonic imaging. When in harmonic imaging mode, the system is transmitting at one frequency and listening to the return signal at a harmonic of the transmit signal. This is 2 times the original frequency. This picture shows a transmission at 3.5 megahertz and a received signal at the first harmonic of 7 megahertz. Note that these frequencies are just examples and not necessarily the frequencies used on the particular system. Harmonic imaging is used to create a less noisy image and to create a much cleaner, crisper picture. As you can see on the image here, on the left is traditional conventional imaging without harmonics. On the right-hand side is tissue harmonic imaging, and you can see that we have a more defined shape to our structures in the ultrasound image. We have come to the end of the abbreviated version of Philips US 9080 Ultrasound Essentials course. If you found this interesting and would like to know more, the full version includes more principles, transducer and imaging knowledge, as well as an overview of front-end and back-end electronics. The full version of the US 9080 is an e-learning and can be found at www.learningconnection.philips.com/catalog. From this page, scroll down until you find biomedical engineers and click on the link. From this page, find ultrasound. Click on the link and you'll be directed to the full catalog of available ultrasound training here at the Cleveland Training Center, as well as the e-learnings that are available. You'll find US 9080 at the bottom of the page. Thank you for attending. We look forward to seeing you soon.
Thank you so much. I have a few questions here, which I will direct to the panel. The first question is, how long is the full version of the Essentials class?
The full version is, it's dependent upon the user because it is a self-paced e-learning class, but it takes between 90 minutes to maybe as much as 2 hours.
Okay, so what if there's a class listed in the course catalog, but there are no dates listed?
Please use the contact us button at the bottom of this of the page for that class, and let us know that you are interested in that class. We try to schedule classes 6 months out in advance, and we also base that upon request for our classes as well.
Okay, that's great. And so what is covered in the trainings that you offer?
As far as product trainings, we cover front end and back end theory. So we talk about the front end, what we call the business end of the ultrasound, how we form the beam, how that's processed. Also the back end, which is the processing, the computers. We also get into theory of operation of all those components involved with that. We get into troubleshooting techniques. We also get into what we call mechanics, how you take the system apart, put it back together. And then at the end of the week, we actually will put a fault or a bug into the systems and let the students use the tools that we've given them through the week, whether it be theoretical or a book or some other tool that may be appropriate to the system, and let them try to work out figuring out what fault that we've put in.
Okay, that's great. Now, has anybody else got anything they say? Mark, Terry, or Jim, have you got anything you'd like to add before we wrap up today?
good on our end, I think.
Yeah, I don't think we have anything we can add to that.
Okay, that's great. So we will wrap it up now. We do not have any more other questions. So I'd like to thank you all for a great and informative webinar. Thank you so much, Stone. And thank you again to today's sponsor, Philips. Just a reminder that the post-webinar survey and certificate process is now automated. So the survey link will be included in the follow-up email, which you'll receive in about an hour's time. Once you've completed the survey, you will be able to download your certificate immediately. One lucky attendee will win an Amazon gift card just for completing the survey. So if you have any questions, please contact us at webinar@mdpublishing.com. And for more information about our upcoming webinars, please visit our website, webinarwednesday.live. So thank you once again for joining us. Enjoy the rest of your day, and we look forward to speaking to you next week for our last webinar of 2019. So thank you once again, everyone. Bye-bye.